One final example of being able to use the definition of Laplace transform, we want to find the Laplace transform of sine AT where A is a real number. So we start by defining Laplace as the limit as c approaches infinity of the integral from 0 to c of sine AT e to the minus st dt. And let's define that as I. All right, that's our integral that we're trying to evaluate, which is really just the Laplace of sine AT. All right, so we'll keep that in our back pocket because we are going to use that a little bit later as we go through this. To be able to integrate this, it's one of those really sneaky ones where we have to do this by parts a couple times. All right, so let's define dv, since we've already done it a few times, as e to the minus st dt. And that means that v is going to be minus e to the minus st over s. Let's define u to be sine of at. And we have our chain rule. And so du is going to be a cos t, or a cos at, excuse me, dt. And so I, which is what we're trying to integrate, is now going to be equal to the limit as c approaches infinity. And we're going to go ahead and use our uv minus integral v du. So uv is going to be negative sine at divided by s e to the st from 0 to c. All right, so what I did was I just swung this dv to the denominator right away. That's going to make it really easy to evaluate the limit, or at least very intuitive as to how to see to evaluate this limit. And then we can just go ahead and use our v du. So minus the integral of v du, and that's going to be a over s cos at, and then we have this e to the minus st dt. And notice that we have a negative right here, and so what we can do is we can just turn that into a positive right away. All right, so make sure you're okay with the algebra. I just put the a over the s, and then just went through and wrote the rest of it. Now let's evaluate this limit as c approaches infinity. And so what happens is when we substitute c back in, so this is actually going to be 0 when we substitute as c approaches infinity. And remember, that's just because when we plug in for t, sine is only going to be between -1 and +1, regardless of the value. And then this e to the minus s, or e to the st, is just going to go to infinity, regardless of the value of s. And then clearly, if we substitute 0 back in for t, then we get sine of 0. So we really get a -0 minus a -0 when we evaluate that. All right. If you don't trust me, go through and work it through for yourself. So in reality, this integral I is going to simplify into the limit as c approaches infinity of the integral of a over s cos at e to the minus st dt from 0 to c. Right? And just like we did before, we're going to have another parts. So we're basically going to use the same parts as we did. So let dv be equal to e to the minus st dt. The antiderivative is going to be negative e to the minus st over s. Let's let u this time be cos at. And the derivative is going to be negative a sine at dt. And so once again, we can substitute into the integration by parts formula. So now I is going to be equal to the limit as c approaches infinity of uv. So that's going to be, and remember we have this a over s that we're dealing with as well. So we have a over s times uv which is going to be, I'm going to do it as we did it before. I'm going to put the e to the minus st in the denominator. So it'll be cos AT divided by se to the st minus the integral from 0 to c. We still have the a over s. Remember, a over s goes to both of those terms inside the parts. And then v du. Notice that we have a negative and a negative, which is going to turn that product into a positive, but we keep the negative out front. So this is going to stay negative, and we're just going to write that as a sine at e to the minus st over s dt. All right. And notice that this goes from 0 to c as well. Right? Now let's just go through and work on the limit, and then we can kind of work on the rest of what's going on here with the rest of that integral. So now when we substitute infinity back in, so we'll just do this one at a time. So as c approaches infinity for this limit, notice that once again we divide by e to the minus st. The value of cosine is between negative and positive 1, so we basically have a constant over infinity, so that's going to be 0. Right? This time, when t is going to be equal to 0. Now check this out. We're going to have a cos of at, which is 1, and then an e to the st, which is also 1. Right? And so what we end up with, and hopefully we didn't miss a sign anywhere here, is we end up with, and I think there should be a negative somewhere. Yeah, probably that negative from this v right here. All right, so sorry about that if I was confusing that. Remember uv v du, there's this negative that should have been in that denominator. So it's a negative 0 minus a negative as times 1 over s. And again, the cosine becomes 1, and this e to the st becomes 1. So they can just basically cancel out, and you're left with a over s times 1 over s. Right? And so that's just going to simplify into, I get rid of all this. So this should just be 0 as it approaches infinity, and this should be negative 0 minus a negative a over s times 1 over s. Or in other words, as t approaches 0, this whole quantity, this limit that we were originally looking at, just becomes a over s squared. All right, so our integral I, and this is going to be the beauty of this integral, is now going to become a over s squared. And then we have minus the limit as c approaches infinity of, now check this, we have a and a, so that's a squared. We have s and s, which is 1 over s squared as well. All right, so we have s and, oh, excuse me, not at s, but the s. That's right here. All right, so we get a squared over s squared of the integral from 0 to c of, so notice that we have sine at e to the minus st dt. All right. Now, intuitively, what we would think is, well, let's just do another parts again. And what we would end up having to do is to just keep doing integration by parts over and over and over and over again. In other words, we would never reach a finite solution. However, very keenly, notice what this is. This integral, if we go all the way back to the beginning, so 0 to c, sine at e to the minus st dt, sine at e to the minus st dt is actually I. So what we can do is we can replace this integral with I. In fact, we can replace the limit, and what we end up with is that I is going to be equal to a over s squared minus a square over s square I. Right? So, and this limit is also part of this integral as well. So the only thing that's not a part is the a square s square. And now we can solve this for I. It's just a regular integral equation, so we're going to get I plus a square over s square I equals a over s square. And we can factor out an I. So we get 1 plus a square over s square equals a over s square. And I know this is looking ugly, but it actually turns out really nice. So I is going to be equal to a over s square divided by 1 plus a square over s square. And notice what we can do is we can just move this s square to the denominator, and we can write I as a over s square 1 plus a square over s square. And mercifully, we get I is equal to a, and we can just distribute the s square plus a square. All right, and remember what I also represented. I also represented the Laplace transform of sine a t. And so this is our answer. It's one of those integration by parts problems where you just have to go through and solve it in terms of the integral. You might remember doing that from Calculus 2. All right, so hopefully that's a good overview as to how to go ahead and compute these by hand using the definition. Now, I want to go back and try to remember some of the answers that we got. So you might remember that we found in the first example that we did a while ago. So this was in the first video. Remember, we took the Laplace of t squared, and that was equal to 2 over s cubed. And remember, we had the Laplace of e to the at, where t was a real number. And I think that was equal to 1 over s minus a. And then we just got the Laplace of sine at, and that was equal to a over s square plus a square. And I want to hold on to these because what we can do, in fact I'm going to try to box these, is these are just a few of some of the common Laplace transforms and the Laplace transform properties. So remember, we just figured out, and you can go back to this, but remember we just figured out that sine of at was equal to a s squared plus a squared. So we just actually proved this one before. And then we had e to the at was 1 over s minus a. We just replaced that with k. Remember we had t squared, and so t squared is equal to n factorial, or in this case n is equal to 2, and divided by Sn plus 1. So it would be 2 factorial over s cubed, or 2 over s cubed, which is exactly what we got if you go up here, 2 over s cubed. So essentially the Laplace transform helps you to be able to verify these formulas. From here on out, unless I specifically tell you to use the definition of the Laplace transform, we can assume that we've proved all of these, okay? And I'm sure you guys could go through and try to prove these. I picked a couple of the easier and one of the more difficult ones just to show you how to do that. All right, so in the next video, what we're going to do is we're going to take a look at being able to find the Laplace transform, as well as one of the transformation theorems of the Laplace transform.